obwohl er nichts gesagt. Nochmal, vielleicht ist zu, ne? Ich denke, wir sind in diese Aufzeichnungsphase, richtig? Ja. Obwohl er es nichts gesagt hat dieses Mal, ne? Ich bin nicht sicher, ne? Okay, I think so, but I'm not sure because I didn't receive the information that we started. It's a little bit strange. But yeah, it seems to be everything connected. Okay, thank you to be here for the lecture of today. Let me restart considering the exercise of last time. Look, the function to be optimized is yeah, I see it in Sie hören nicht. Lautstärke aeroben. I don't understand everything it seems to be okay here. I cannot change. I hope that is okay. I hope it is okay, but I'm not sure. Chat. It is recording. Oh, thank you for the confirmation. About the microphone, I don't know what you intend. I hope that you can hear me. I don't know if I can hear you because you didn't test, but I think so. Okay, the function to be optimized is, okay, thank you. The function to be optimized is x squared plus 2 times y squared, constrained with g of x comma y, which is x plus y equals 100. Let me try to interpret this problem in a possible economical context. And then we will see geometrically what I can say, how can be interpreted, and then we do this together. Interpretation. Assuming that x squared plus 2 times y squared represents the cost of production per day for 2 products. I have a company with 2 products. Of course, practically very often the company produces many products. If I have a X, Y, Z, W, we need a computer to do this exercise. I don't have time to show you how we can program a computer, but you can understand that it's still relatively complex to solve with 2 products. If I have more than 2 products, we need a computer which help us to calculate the gradient, to calculate the rest. But let me go ahead. X is the cost of the piece of an element. I don't know, do you remember last time I told you I am producing radios and TV, monitors, and I don't know what. Just 2 products per day is the cost of X product in the category per day, and Y is the cost of another category per day. 2 possibilities. Of course, in the real application, the function probably is more complex. Why here we have the weight 1, here we have the weight 2. This is just a mathematical exercise. We are here for math, for engineers. This weight and this weight here must be calculated by the chain of production. Typically, this is the problem of the chain of production. It's not a problem for a mathematician. But assuming that we are able to say that we have the cost that, let me say, increases squared for X and Y product per hour, per day, it doesn't matter what. Could be per hour, could be per day. But with different weights, weights 1 and weights 2. This should be identified through measurements. This is complex, of course, these 2 parameters. I'm not economist. I cannot tell you how we can do that. But assuming that we have this value from expert of the production chain. And we want to calculate the minimal cost for this two production. Minimal cost means what is the number of pieces of element of X, and what is the number of element of Y per day, for instance, in order that the cost of production is minimal, assuming that, the number, X is the number of product of X per day, and Y is the number of product of Y per day, equals 100. This means I would like to calculate the minimum cost. If 100 is the maximum, for instance, is the maximum production per day in my chain, but I have to decide how many X, how many Y. I don't know if I was able to. I'm not good in economy, believe me, absolutely. But because first of all, I don't have idea how we can. I am a little bit from control system for system theory, but I don't want to tell you because I don't want to make mistakes in the what I'm telling you. The coefficient 1, the coefficient 2, and not only Y squared. This is an economical problem. Huh? Why the cost increases up to square? But I have seen something like that. Here is a little bit more comprehensible. No, we have two possible chain of productions of two products per day, and the maximal production is 100. And I would like to use my maximal power of production, 100, but I don't know how many X, how many Y. In order, what is the goal? To minimize the cost of production. The goal is to minimize the cost of production in this problem here. Of course, the goal could be also a different economical goal. To find the maximal production per day. That I'm not expert of this, but mathematically, to find the minimum, to find the maximum, you remember the theoretical part of last time, is quite similar. Because using the gradient, we can find the candidate solution in case of maximum, in case of minimum, and then we classify, could be minimum, could be maximum. I don't know if you remember high school, the derivative. I try to recall you high school knowledge. The derivative characterizes minimum and maximum. The derivative to zero. Do you remember this? If you have a parabola, let me say, in a convex parabola, the derivative to zero is the minimum in this case. If you have a concave parabola, the derivative is the maximum. This means the derivative to zero, excuse me. The derivative to zero characterizes both. Then we have to look at the second derivative. It's quite similar, but of course, we can see the problem a little bit more complex because we have two variables in the function. This means we speak about gradient. I don't know if you remember. I will repeat again, which is the vector characterized by the partial, nevertheless, derivatives. I will do it exactly now. This is a little bit the meaning and the possible interpretation. Look at the geometric interpretation. Do you remember before last week, we concluded a little bit with plane, hyperplane, line, and so on. And this sense can help also to figure out what happens in a geometrical sense. This is nevertheless is useful because we can figure out approximatively in this case quite precisely because it's relatively easy to build the scenario in geometric sense. We have the paraboloid. I don't know if you remember Math 1 or Math 2, but it doesn't matter if you don't remember, which is basically is a parable, let me say, characterized by X and Y, which we can see in 3 dimensions, something like that. If you don't remember, if you don't know, it does not matter. What you should remember, nevertheless, is the plane X plus X equal this plane here. Let me see. X plus Y, or Y plus X equals 100. I don't know if you remember this. I told you. I will repeat again a little bit to figure out. Figure out is important because we have a better feeling what we have to find. And again, some student ask me if I ask some graph in the examination. No, I don't ask. The graph is important for you if you want to figure out a little bit, if you want to verify or to validate what you are doing. Also, for me, it's difficult to draw, believe me. Yeah, let me go ahead. The plane x plus y equal 100 can be seen as in a plane. I don't know if it's visible, this red plane parallel to z. Let me interpret it a little bit in another form, this red plane. Think about, I wrote here, the line now, y equals minus x plus 100. It's interesting what I am saying, because this equation here is in the meantime as in a line, as in a plane. This will be confusing. I don't know. Before I told you, x plus y is equal 100 is in a plane, which is parallel to z. Now I am saying y plus x equal 100, the same, or if you want, I can write in this form here, but it's the same. I don't know. Y plus x equal 100 is the same, no? It's in a line. It's in a line, it's in a plane. It seems to be a little bit confused. Now, do you remember I told you this? It's not confusing if I think that y plus x equal 100 or y equals minus x plus 100 in 2 dimensions is the line. Because if I consider this expression in 2 dimensions, in which I don't consider at all the existence of another dimension set, it's clearly in a line. Gymnasium, Math 1, Math 2, I don't know. Y equals minus x plus 100, I think no problem to draw. It's exactly what you can see here with this dashed blue line. Now, y, in order to remember the red set, which is in the plane, is in the plane, first of all, and is parallel to z. I don't know if you remember the lecture when I introduced the hyperplane. Yeah, if I assume that my environment, my room is in a room in 3 dimensions, this means I assume that z exists. I mean, x plus y equals 100. If I assume that z exists, is valid for each z, because I don't characterize in the equation z. Z is not included. For each z means geometrically something which is parallel to z. Think about what I am saying. Y is parallel to z. Can be seen in if you want in different form. But let me. It's interesting for you if I clarify this before going ahead with the optimization I would like to do, because sometimes this is not clear. Also for the exercise, the geometric exercise. No, when in the case we want to solve some exercises in the context of analytical geometry. I show you why. Because probably it's not totally explicit that the red plane characterized by x plus y equal 100 is parallel to z. If I am considering 3 dimensions. And this dashed blue line is the trace. You know the trace? In German is Spure. Is the trace, understand what? Of the red plane on the plane xy, which is the plane z equals 0. The plane xy for each x and y is the plane characterized by z equals 0. Look, do a little bit to interpret what I told you until now. Did you agree with this? In two dimensions, vector V equal 1, 1 is orthogonal to the line. I don't know if you remember, because it's the gradient of this. I don't know if you remember. This coefficient here, this coefficient here. Did you agree? Now, let me consider the z-axis. Did you agree on this? I told you why. No, this coefficient here, this coefficient here is the gradient. I told you, I did also some exercise in order to justify that's one, which is the gradient of this expression is orthogonal to the all points of the line. Okay, assuming that you remember, otherwise you can, let me say, reconsider again. Let's consider now the z dimension, or the z dimension. The dimension characterized by, let me say here, vector L line. Vector Z is characterized by 0, 0, let me say 1. The direction of Z could be also any kind of element here in this position, but let me consider the unit vector which, let me say, characterizes this direction. Now, as I told you, this line here, if you consider the system or this representation in two dimension, at this vector orthogonal at all points on this line here. Now, if you remember that Z is orthogonal to the plane X and Y, This means, and the plane X and Y is characterized, let me write. X, Y, let me say, is characterized by Z equals 0. This means that if I consider, I write so it's clear what I intend. The set X plus Y equals 100 in 3 dimensions, then the vector orthogonal to this line is because the line lies on the plane xy, which is characterized by z equals 0. Could be also improved this way too. I wrote very quickly, but I think it's clear. Because as I told you before, it's characterized by z equals 0. Everything which lies on xy. But of course, if I consider that this is included in another, let me say, point of view, or consider the three-dimensional point of view, this is the